Hello class. So in this video, we'll continue on section 6.1, and I think I will let you know when we switch sections, but I believe this is all still section 6.1. If not, I'll let you know later. But as I mentioned before in the first video on this chapter is that we'll basically cover as many sections as we can until we run out of time or until I think we've covered enough and we can move to other topics, other selected topics. Okay. So in the previous video, we saw that the Laplace transform as a function whose domain is functions defined for t greater than or equal to 0, for which the Laplace transform exists, which is the same as saying that this integral converges, right? And whose range are some functions of s. Right? We don't know what they look like, but we know that they're expressions involving s. So this Laplace transform as a function is linear, right? Meaning that we can move constants outside and we can separate the sums, right? The sums or negatives, doesn't matter if it's plus or minus. And then, of course, we also mentioned that it's similar to what happens with derivatives and integrals, right? Both derivatives and integrals are linear functions. So if you think of them as functions, they satisfy these two conditions, right? That you can separate the additions and you can move constants outside, right? So any function that satisfies those two conditions is said to be linear. Now let's use it to actually calculate examples, right? So I'm going to do A, and I'm going to let you do B as classwork. Actually, as an exercise. So this is for last semester, last summer, when we actually had face-to-face. This is going to be an exercise for you. But I'll go ahead and do A. So I want to calculate the Laplace transform of 1 plus 5 times t. Well, we know that the Laplace transform as a function is linear, meaning that we can separate the sums. Right? So it's the same as the Laplace transform of 1 plus the Laplace transform of 5t. Not only that, but also because it's linear, we can move constants outside, meaning that this is just the Laplace transform of 1 plus, we have 5 times t. Let's move that constant outside. This is 5 times the Laplace transform of t. In the previous videos, we already found what both of these Laplace transforms are, right? We found that this was equal to 1 over s plus the Laplace transform of t is 1 over s squared times 5, so 5 over s squared, with the restriction that s is greater than 0. Right? We had to use that assumption so that the improper integral actually converged. But that's the idea. As long as you know the Laplace transform of functions that you're adding or subtracting, you can just evaluate the Laplace transform of each. And if you have any constants multiplying your functions, you can move those outside. So a very nice property, very useful. We don't have to go ahead and use the definition to compute this whole thing, right? We don't have to plug in the integral, the improper integral of either negative st times 1 plus 5t dt, because if we know each of the parts, we can just separate the sum or difference and move the constants outside. Okay? So a very useful property. Now, we're not going to be computing all of these by hand, right? Because, well, it's a lot of work, and a lot of them actually have pretty nice formulas. So in this theorem, I'm basically going to give you the Laplace transform of some basic functions. Now, I should have included some restrictions here. For example, s greater than 0, etc. So actually, I don't know why I did not do that. So let me check. Okay, so I checked, and yeah, the theorem in the book doesn't have any conditions on s. We'll see other conditions on s. So for example, we saw that for t, s has to be greater than 0. I believe that for t of m, s has to be greater than 0. Now, the reason why the book doesn't give you these values of s, so it's basically asking what's the domain of this function 1 over s, what's the domain of this function n factorial over s to the n plus 1. The reason why they don't give you that is because for most purposes, we won't really be working with what s is. Right? So is s greater than 0, greater than 1, greater than 2, is it negative? We won't really be working with any of that. We're just going to be working with these as expressions, right? So not really worried about them as functions, meaning that we don't really care what the domain of these functions is. Now, it is important, especially in theoretical work, right? Because as we saw, this Laplace transform is only of 1 is only equal to 1 over s, is we assume that s is greater than 0. Right? So there are some, the fact that S has to satisfy some properties is included in there. for most purposes in this class, you won't really have to worry about what S is, so what the domain of the function is at the end. So again, that's why they don't include it in the theorem in the book. Okay? So again, here I'm giving you a list of common Laplace transforms. And here I should say that K is a constant. So A, K, yeah, where A and K are constants. So the Laplace transform of 1 we saw is 1 over S. The Laplace transform of t to the n, where n is either 1, 2, 3, etc., is n factorial over s to the n plus 1. And you see that this works when n equals 1, because 1 factorial is 1, s to the power of 1 plus 1 is 2. So we do get that the Laplace transform of t is 1 over s squared, which we found in the previous videos. The Laplace transform of e to the a times t is 1 over s minus a. The Laplace transform of sine of a constant times k, well, you can bring the constant outside, and you're left with k over s squared plus k squared, and etc. for the other ones. These are the functions that we're usually going to be working with when working with the Laplace transforms. Right? So now that I've given you these tools, or this theorem, if I don't ask you to compute a Laplace transform by hand, then you don't have to do it. You can just go back to this theorem and look over it. And for the final exam, which is just exam 2, I will give you this table. Right? So you don't have to memorize this. Right? So again, let me say you don't need to memorize, you can just use. Including for the exam. I will give you this as a note sheet. Oh, I was thinking about when we were face to face. Okay, so you have your notes anyways, but I'll still give you a page with these common notes that you're going to need. Okay? So you need to memorize and just use this theorem unless stated otherwise. So just use this theorem unless stated otherwise. Right, so unless I say use the definition of the Laplace transform to calculate the Laplace transform of this function, if it's one of these common functions, just go ahead and write out what it is based on this theorem. Okay. And again, there are restrictions on S on some of these, and some of them there might not be. However, again, for our purposes, for a lot of the work we do, we're not going to be worried too much about what S is. In the previous or in the next videos, you're going to see that there are some restrictions because we're going to talk about when does the Laplace transform of a function exist. We're going to see if we can give a general way, like say, okay, if a function satisfies this property, then the Laplace transform exists. Right? So we're going to talk a little bit about that. And then you're going to see again some conditions on S showing up. But when we're actually using this to solve differential equations, the domain of the functions that you get, the functions of S, is not going to be that important. So that's why it's not listed in this theorem. Okay, so in the next video, we're going to talk about when does the Laplace transform of a function exist. Again, can we give a general property that all functions that satisfy this property, we're guaranteed that the Laplace transform exists. Okay, so we're going to talk about that in the next video.